This recording is the recording of Module 9 regarding the cost at neighborhood level within the course Economic and Sustainability Aspects of Architectural and Urban Design. This module is a follow-up of the previous one on cost calculation at building level, so now we will enlarge the scale to the neighborhood level. Some important dates. First of all, it was foreseen that you would present your cost analysis on the 26th of November. We will change it. It will be 1 week later. So on 26th of 11 there is no course, but we do have a final session on the 3rd of December. Furthermore, the date for the oral exam is by now planned. It will take place on the 18th of January. And the paper deadline is on the 8th of January. The module on cost calculation at neighborhood level aims at stressing the importance of densities when calculating the cost of a building. Hence, we make a link between the cost at building level and the neighborhood level, and we will introduce a cost calculation tool for the estimation of the cost at neighborhood level. The module is structured as follows. First of all, we make the step from building to neighborhood level. We look at parameters that can represent the density. Then again, we will make or develop an abstract model of a neighborhood, parallel to what we did at building level. I will introduce the cost calculation tool. We will look at some unit prices for infrastructure and the ratios that are important at the neighborhood level to finally end with the intermediate task. And the final task of this course. This recording only focuses on the first two parts, the step from building to neighborhood level and the parameters that can represent the density of a neighborhood. When we look at the built environment, we saw in the previous session that buildings can be subdivided in components, in smaller entities. The first component that we were looking at was the component or the element level. These elements are functional, independent elements that an architect is accustomed to work with, as for example outer walls, windows in an outer wall, the roofs, and so on. We also saw that each of these elements can be subdivided again in different work sections or processed materials, and each of these processed materials again consists of different materials. So this hierarchical subdivision of a building into smaller entities, we can also take the same approach but to the higher scale levels. So a neighborhood does not only consist of buildings but also consists of infrastructure, streets for example, but we also need ducts, we need the sewage system and so on. And even one scale higher, this neighborhood fits in a higher entity, in a larger scale entity like cities, towns and so on. So the same principle of subdividing the built environment in entities is again done here at the neighborhood level. And that's what we're going to do when we estimate the costs. Now, first of all, before we go into the cost estimations, let's have a look at different parameters that exist to define the density of a neighborhood. In literature, different parameters can be found. So first of all, we need, before we look at density parameters, we first need to define some terms that are important and that are used in these different parameters. The first important data is the land area. So the base land area, it's the full area where we're going to build on. So it's the ground floor which is available for building, which is here indicated with the letter A. We also have streets. We need streets in the neighborhood and surrounding the neighborhood. So the dark green or the full lines are the network streets, the streets which are located in the neighborhood we are looking at, and which means it serves only for the people that are living in the neighborhood. While of course this neighborhood is connected to a larger system, the city or a town, and hence there are also streets or infrastructure in general connecting that neighborhood to the other neighborhoods, and hence these networks are shared between this neighborhood and the neighboring or the bordering neighborhoods. We need to know hence what the network length is of the streets in the neighborhood and the ones surrounding the neighborhood. This is indicated with the letter L. A third term is the gross floor area. It means it's the area that is used by the residents or by the office workers or so on. So it's the total floor area on all floors being built. This is the gross floor area indicated with the letter F. And the last parameter that will be important to define densities is the built-up area. So it's like the physical footprint, only the ground floor of the built area, indicated with B, from built-up. These different terms will be used to define the density parameters. A first density parameter is the floor space index. The floor space index refers to the building intensity, and it is calculated as the ratio of the gross floor area to the basic land area. So we subdivide the total floor area of all the layers in our buildings in the neighborhood by the available land area. This is called the floor space index and is a first density parameter. A second density parameter found in literature is the ground space index. Now we only look at the physical footprint of our buildings, so the ground floor footprint, and we divide it by the baseland area. So if we would only have one floor, it means that the previous indicator, namely the, I'm going forward instead of going back. Excuse me. So the floor space index and the ground space index are identical when we only have one floor and we only have the ground floor. As soon as we have more levels than just the ground floor, we have a different ground space index compared to the floor space index. So the two are different as soon as we have more than one built-up layer, so as soon as we have more than just the ground level built. A third density parameter is not on the buildings, but is on the network. So how much infrastructure do we need to serve our buildings we are building? So the network density characterizes the concentration of the networks in an area and is calculated as the ratio of the network length to the baseline area. So what we need to know is how many meters. So what is the length of the infrastructure serving the neighborhood compared to the baseline area. You have to be careful in the sense that the internal roads and the internal infrastructure is only used by the residents in the built-up area and hence is fully accounted for, while the surrounding infrastructure is not only used by these residents but also by the ones living on the other border of the street. And so only half of these infrastructure lengths are accounted for. So to explain that graphically, if we look at this picture and we have 4 buildings, we have streets surrounding the neighborhood and we have streets crossing the neighborhood. Well, for the surrounding infrastructure, we only account for half of the street because the other half is serving also the other neighborhood, so it's a 50-50% allocation, while it is assumed that the roads crossing the neighborhood are only used by the residents in the neighborhood and hence are fully accounted for. So in length, we account for everything, but in surface, we count for half. Or we can also account for half of the length if we want to take into account the fact that it's a shared road between 2 neighborhoods. So that is a choice to be made depending on the goal of the study. The network floor index is the next density parameters. And now it does not subdivide the infrastructure by the baseland area, but subdivides the infrastructure, so the length of the roads, for example, by the gross floor area. So it's rather a link between which infrastructure is needed and how many people or how many square meters of floor area is served by these infrastructure. So it's the length of the internal and external network divided by the floor area. And for the external network, only half of the length is accounted for to allocate part of it to the neighboring neighborhoods. The last density indicator is the population density. It's the number of inhabitants divided by the base land area. And it's expressed as inhabitants per hectare. It's a bit the same as dividing the gross floor area, dividing by the baseland area, but it is a differentiation in the sense that if the square meters of floor per person is different, then it might lead to a different number if we compare two neighborhoods. Let's see now if you apply these different density indicators to three different urban fragments, what we can learn from it. So the first urban fragment is a typical residential neighborhood in the Belgian context, where we have detached houses, every house surrounded by its own garden. The infrastructure needed for this neighborhood is only the surrounding road, because there is no road crossing through the neighborhood. So here we only have an external infrastructure. So this view can be translated into a plan as well. So we are looking at a detached house in a neighborhood of detached houses surrounded by an external infrastructure. A second urban fragment are terraced houses. So we see here an urban block consisting of terraced houses with inner gardens surrounded by these buildings. There are no internal roads, so again we only have external infrastructure. This is the plan, so we have a terraced house with its own private garden, and this is the external infrastructure serving this whole urban block. The third one are three apartment buildings served or which you can reach by this street level surrounding the blocks. We have the apartment buildings and we have here some garages, and these are the external roads. This is an internal road and this is an internal road. For the three neighborhoods, the four or five density indicators have been calculated. In the bars, which are presented on the left vertical axis, you see the network density in orange, the floor space index in gray, the ground space index in yellow, and the network floor index in blue. The lighter blue dots are shown on the right vertical axis and are the population densities. It is the number of inhabitants per hectare. What we can see if we compare the three neighborhoods, so a detached neighborhood, the neighborhood with the terraced buildings and the neighborhood with the apartments, that we see quite some differences in the different density parameters. So first thing that we clearly see is that the population density and the floor space index follow the same trend. So the floor space index is the ratio between all the floor surfaces, so not only the ground floor but all the levels, divided by the available plot, so the available land. And the population density is the number of inhabitants per available land. So if the number of square meters floor per inhabitant is the same for the three dwellings, it is logic that this trend is identical. Only if one of the three models would have a very different size of housing per inhabitant, we could see a difference between the two density indicators. If we look at the network density, it is the same more or less for all. There are small differences, it's also a small number. We have not so much road or infrastructure per square meter of land. Why? Because we only have an exterior infrastructure and no interior infrastructure in the block. If we compare the ground space index and the floor space index, so the gray one which is increasing over the tree, with the yellow one which is not increasing over the tree. So we see a clear difference here with the apartment compared to the other. So it means that the apartment buildings have a smaller physical footprint. So the ground they take as a building, so the ground floor surface is smaller than for the terraced house and a detached house. So if you look at the full plot, the amount of area that is taken by a building, by the built-up area, is smaller in the third model. And of course also in the first one, but it's higher in the terraced building. So if I go back to the pictures, so here it's this area, the green, 1, 2, 3 times divided by the full area. That is what this ground space index means. And then the final one, the net floor index compared to the first one, it's the difference. Now we divide the number of the length of the streets by the amount of floor, taking into account all floor levels, while here we only took into account the floor available, so the buildable floor, the plot size. And we can see, of course, in an apartment building, while these were all the same more or less, an apartment building you have many more levels, so it means we have many more built-up area per per available land area. So the gray one is very high. It means that this one, of course, is very low because we subdivide the same amount of infrastructure over more build-up floor area, but then taking into account all floor levels. So the different indicators give different kind of information. So it's important to link, if we talk about density, to carefully think about what is behind the indicator. And with this slide, I would like to end the first part of this lesson on costs at neighborhood scale.